Okay. Well, thanks very much for inviting me to give this talk. It's been fun to prepare it, and it's kind of an honor to discuss my research to such a broad audience across the globe, so that's kind of cool. I also want to straight up acknowledge that I stole all of this work from my grad student, Dennis Felixson, who I believe has logged in, so he can be here to answer all the questions. He did this work for his PhD, and he's moved on now. He's a NASA scientist. We also worked with Tim Bartholomew and Mathieu Morlahem at UC Irvine to help develop the ideas that I'll talk about today. And so I'm going to motivate you with the thing that we're all motivated by, which is really trying to understand how sea level rise is changing over time. But I want to convince you that sea level rise is already happening. And this is data that comes from tide gauges on the eastern seaboard of the United States. And it just simply shows when those tide gauges are experiencing flood during just high tide events. So these are called sunny day floods. They're occurring regardless of the fact that there's a storm or any kind of storm surge. They're just occurring because they have an increased baseline or increase in sea level. And you can see already that many of these towns are seeing these increased frequency in flooding of sunny day floods during high tide events. And we know that one of the larger contributors to sea level is the Greenland ice sheet. This is GRACE data, a wonderful data set that has been laboriously picked through. And we can see lots of details in this record, changing mass balance over the annual cycle. But on average, Greenland's losing about 280 gigatons of ice per year to the ocean. And a lot of that is draining from the periphery of the ice sheet. And so if we want to be able to project into the future what sea level is going to be, we need to make this connection between the climate driving changes in the ice sheet and how the ice sheet responds. But the problem is that it's a multi-scale, multi-physics problem. There's processes that occur over a wide range of spatial scales and time scales that we need to take into account. So we need to look at things on this large scale where climate, both the atmosphere and the ocean, are influencing glaciers, all the way to the tiny scale at the terminus. And so at this large scale, we know the atmosphere has been warming. This is data that comes from Luc Trussell, who had some ice cores that were reconstructing melt of the ice sheet. So it's here called runoff. And melt has been increasing since the late 1990s, and this is corroborated in a number of regional climate models for Greenland. We also know that on this large scale, the ocean heat content in the North Atlantic has been increasing, and that's also been warming since the late 1990s as well. This brings a lot of heat up to Greenland, which then circulates around Greenland now at a smaller scale. We're interested in how these currents, in this case, I'm looking at the West Greenland current, transports this heat around the west coast of Greenland. And it's important to understand things on this scale because the heat is actually at the bottom of the ocean column because it's really salty. And so it sinks to the bottom and it can make way to the glacier terminus because of these deep troughs that are in the continental shelf. Those troughs were formed during the last ice age when the glaciers had coalesced and moved out to the continental slope. And so it's those deep troughs that allow this water to easily make its way to the glacier termini. When we get to the fjord scale, there's a whole host of processes that are at play in the fjord, and it's really this interaction between the ocean properties that influence the glacier and the glacier terminus, but then also processes that happen on the ice sheet as well that can influence the fjord hydrography. And we need to understand all of these processes if we're going to try to link the ice and ocean models in a kind of a two-way exchange, so how the oceans impact the ice sheets, but also how the ice sheets might impact the global oceans. And then we get to my favorite scale, which is glacier termini. And this movie really nicely demonstrates how complicated glacier termini are. They adjust on a range of time and space scales. They're really challenging environments to work in. And so we've done a lot with remote sensing to try to understand these environments. They're also, most of the processes are happening in the submarine environment. So you can't see very much from space, so you have to infer a lot from space as well. So it's a really challenging environment. But the other thing that's kind of interesting when you look at things on this scale is that it's not just the atmosphere, the ocean, and the ice sheet, but also the substrate is important as well. And these termini are very susceptible to changes in geometry, and I hope to show you about that today. So I'm going to show you some examples of changes in Greenland that have been happening over the last few decades. And what we see, so this is work that TV's done showing terminus retreat largely in red for all of Greenland, Greenland's outlet glaciers for the period 2000-2010. And you can see that there's a lot of red, so a lot of glaciers are retreating, but within that red, the spread of the size of the circle is quite variable. So there's some glaciers that are retreating a lot more than others. And then there's also a few blue circles, and that shows us that there's some glaciers that are advancing. So there's quite a bit of complexity to the story of the climate perturbing glaciers. That complexity arises also when you look at elevation change. So this comes from Beasato, and she's looking at individual glacier elevation change from her reconstruction. And you can see thinning glaciers here in pink, and that fits into our mental model of the climate is impacting the ice sheet, that the glaciers are retreating, they would thin and steepen and accelerate. And that's what we see in these pink dots, but then there's a whole bunch of other points here that are colored with all kinds of different things that I won't go into. But that really complicates our picture of how glaciers are evolving over time. And the same is true when we look at surface velocities. This comes from Twila Moon, and it shows the surface velocities from INSAR. And just look at the circles for West Greenland and East Greenland over these different time periods. And you can see glaciers that are accelerating, and then they decelerate, and then they accelerate again. And you see glaciers that are accelerating right next to glaciers that are decelerating. And so when you have over 200 glaciers in Greenland that you're trying to predict the future of, and then you also see this exhibited heterogeneity in the dynamic response, the question is really how well can we predict them when they exhibit this kind of complexity? And this was really the motivating question for the work that we did in Central West Greenland, is to try to understand why is it that these glaciers have such differing dynamic responses. And so we focused on this area in Central West Greenland that is pretty typical of most of the ice sheet. There's 15 glaciers here. They exhibit a whole host of different dynamic responses. And these are data sets that we've put together of terminus change and elevation change. And I'm going to start out by talking about the terminus change. And so this is what it looks like in map view, all these glaciers, and here's the time series. And these were hand digitized glacier termini by a whole bunch of undergrads. And now we're working to help to improve the automation of termini extraction from imagery so that we can serve this kind of data and no one else has to ever handpick a glacier terminus again in the future, hopefully. But the cool thing about getting every possible terminus data point that we can is that we can really see a lot of variability in the terminus position over time. So there's both variability in how much the terminus retreat has happened, but then there's also all this temporal variability as well. So the interesting thing is that most of the retreat that happened in this area, the long-term retreat, occurred simultaneous with the increased air and ocean temperatures that I talked about earlier in the late 1990s. And so we suspect that there's some kind of regional climate perturbation, but we can't really deduce from this the exact process responsible. We can only say that it was regionally synchronous, so it must be some sort of external climate perturbation. So the idea is that it's possibly the warming ocean and the increased melting on the surface that have combined together to create more melt at the glacier terminus. So the interesting thing to me is that not all glaciers have retreated. So there's only, there's 70% of them that retreated, but 30% have not retreated, and they've remained stable in the face of this climate perturbation. And then there's quite a big spread in how much retreat has happened, which is typical. It's what T.B. Murray saw as well in her study. And so what I want to try to convince you of today is that the climate is pushing glaciers into a new dynamic state, but it's really the local geometry that's controlling the magnitude of how much change actually occurs. And this is not really a new idea. This is just the marine ice sheet instability, but for really small fjords. And this was proved theoretically by a number of authors in the 60s and 70s. And the idea is that a glacier resting on a reverse bed slope is more susceptible to a climate perturbation. And I pulled out this quote by Terry Hughes because it's really a wonderful quote. It says, "Hence, a relatively minor climatic fluctuation along the ice shelf calving barrier can unleash glaciodynamic processes independent of climate that can cause calving bays to remorselessly carve out the living heart of a marine ice sheet." I love that one. Okay, so this is all I'm talking about, but we've never really had the observational data before to examine it on this kind of scale until Mathieu and his group put together this new bed topographic estimate for Greenland. And this is an estimate based on mass conservation techniques. They use all the radar data that's available for ice thickness beneath the ice sheet, and then a whole host of bathymetry data for the fjord depth in front of these glaciers. And that allows us to get a pretty seamless transition in the topography estimate of the bed at the terminus position. Now, it's not a perfect data set, but it's really the best that we can get right now. And in my examining of this, it appears that it does represent the shape of the bed really well, which seems to be the most critical factor for controlling dynamics. So let's look at a couple of examples. This first one is called Umiyamako Ispray. It retreated about 4 kilometers in the time period of 2001 to 2009. And then it stopped it's still stopped in this new position for a while. So it's pretty anomalous, short period retreat and then stabilization. But when you look at it in the context of the topography, it makes a lot of sense. So this is a map that shows the Landsat background. This has the mass conserving bed. This is underneath the ice here, and then this is underneath the ocean, and here's the terminus position. And then this is just along the glacier flow line, the center line, showing the bed topography on average across the width. And then it's colored by the bed slope. So where it's black, it's a negative or a positive bed slope, and where it's red, it's a negative bed slope. And so we can kind of watch this terminus evolve over time, you know, in that it hasn't received the climate perturbation yet. And so it's got all this seasonality, it's moving back and forth. But as soon as it gets into this red zone of the terminus, this reverse bed slope, it retreats all the way until it gets to a new stable position. And you can see that it ignores these smaller places of positive bed slope. And that's because the seasonality is so big that it can effectively just wipe through that area without really sensing it. And so we can see another example. This is a more modest retreat. This glacier called PERD, our little acronym for it. And this one has a much more obvious kind of bathtub behind it. And again, it's pretty stable and seasonally variable until it starts to get perturbed by the climate. And then it gets into this area, really negative bed slope, and retreats back, ignoring small areas of positive bed slope until it stabilizes on this area where the bed is really extremely positively sloped. And so you can really just merely look at this length scale of this overdeepening behind the terminus position and estimate how much retreat you'd expect from that. And you get a pretty simple relationship, this one-to-one relationship between the overdeepening length behind the terminus position and how much retreat happened, and you get a pretty decent fit. So then you can look in the future at the next length of the overdeepening to see what would we expect if the glaciers were perturbed again. So retreat only tells us kind of half the story. And this was an important paper that was written by Steve Price and others in 2011. And what he did was he looked at the largest 3 glaciers, largest flux 3 glaciers in Greenland, and perturbed the terminus of those glaciers and looked at the sea level contribution from those. And so it's called this committed sea level rise based on what happened in the last decade from 2011 perspective. And what he found was that most of the sea level rise comes from this long-term diffusive response of the ice sheet. So you perturb it, but then that sets up a thinning wave that propagates inland over a much longer time period that contributes to sea level. And it's really this elevation change or thinning of the ice in response to that perturbation that we really need to understand as well. And so that's where this additional data set comes in, this elevation change data set. And this is what my student Dennis had worked on extensively for his PhD. And I'll tell you a little bit about how we got this data set. But first I'll say that this also exhibits the same kind of heterogeneity that we see with the terminus change. We had some glaciers that are thickening and some glaciers that are thinning. But then we also see this kind of curious relationship where a glacier like Ingia that's retreated nearly twice as much as Umi has thinned half as much as Umi here. So this is Umi here and that's Ingia. And so the question is, you know, why is it that they are not related to one another? You perturb a glacier, you would expect it to thin a commensurate amount. And so my student Dennis took 2 DEMs, and these are really high resolution DEMs. One is a WorldView DEM, and then that's from 2013, and another was an air photo DEM from 1985. And he differenced those, and then he subtracted out the surface mass balance, which is shown here on the left. And this comes from RACMO, a regional estimate of surface mass balance, and it's been downscaled so that you can nicely resolve the surface mass balance product in these fjords. And so we subtract that out, and this elevation change really then is just the dynamic component of the elevation change. It negates surface mass balance. Okay, so we applied Nye's theory of kinematic waves applied to glaciers. In his earlier papers, he looked at accumulation anomalies and how they would manifest and move on an ice sheet or glacier. And we're looking now instead at terminus perturbations, but the same ideas really apply. So the idea is that we treat this glacier terminus, and that sets up a thinning wave which propagates up glacier some distance. And these perturbations can both diffuse, so they'll spread out. And because the perturbations initiating from the terminus, that diffusion is primarily going to happen in the upstream direction. Perturbations can also advect with the flow, and that is going to primarily happen in the downstream direction because of the high slopes associated with coastal Greenland. And so we derive this Peclet number, which is this non-dimensional expression that relates how much advection is happening to how much diffusion is happening multiplied by this length factor. And this is really, once you do the math, is proportional to just geometrical constraints of the ice. So the surface slope minus the thickness gradient over the thickness along flow for these glaciers. And so in a case where we have a high advective transport rate, a perturbation at the terminus is arrested as it goes upstream, and it can't propagate inland very far. In the case where we have a high diffusive transport rate, that allows diffusion to move very quickly into the interior, very far into the interior without any kind of impedance. And so we can look then at an example. We'll look at this one, Kangerlingata Sirmia down here. Here are the two DEMs, this 1985 one, and then this present day is 2013, and then the mass conserving bed is down below. And we can do the difference between these two DEMs to get this dynamic thinning, so how much the elevation has changed in a center line for this area, and there's some error on that. And then we simply assume that the elevation change is uniform across the glacier to get this value, which is a % unit volume loss. And the idea here is that we're just looking at like, where's most of the volume lost from? So downstream of a point that's kind of in this orange zone, like in here, about 50% of the volume loss would have occurred. But downstream from these yellow points, about 100% of the volume loss would have occurred. And then we take our geometry and we calculate our Peclet number, and we get this value in black. And I've highlighted these red areas because these red areas are higher Peclet values than downstream Peclet values. And the idea here is that when you have a higher value than the downstream value, that's an area that will arrest any kind of diffusive thinning from propagating inland. So you'll have a perturbation, where's my mouse? A perturbation downstream, and that can propagate to about here, and then it'll be arrested a little bit in this high advection zone area. If it makes it up to here, it'll diffuse all the way up to here, and then it will be arrested a little bit more up here. Okay, and it kind of makes sense if you look at the geometry. Advection is high in this area where the ice is thinner, and there's a steep bed bump that forces the ice to kind of move down this flow. And let's see, this is kind of analogous to a waterfall. You can kind of imagine if you put dye in a bottom plunge pool of a waterfall, that dye is not going to easily diffuse up the steep waterfall. But if you put the dye in the top of the waterfall, it can easily advect down with the water into the plunge pool below. And so we're interested in these areas where advection is arresting that, that thinning wave from propagating. And so we extracted out these red values in the Peclet number, and we call those the Peclet running maximum. And then we also extracted in that same location the % unit volume loss. And we did this for every glacier that was thinning. And we get this plot here that shows for, I think it was just 12 or 13 glaciers that were thinning, but they all have this same pattern that shows that once you get to a Peclet value around 3, that most of your volume loss, 90% of your volume loss has occurred downstream of that point. And so if you plot all the different Peclet points for these different glaciers, you see this heterogeneity. You see that Umiyamako up here has a Peclet point of 3 that's much farther inland than neighboring Ingia. And that's why this glacier can thin a lot more, even though the perturbation was a lot less than neighboring Ingia. And so Dennis has recently taken this work and expanded upon it by looking at all glaciers in Greenland that we can. And this is based on where the mass conserving bed data really allow us to make inferences about the bed topography. So there's just 141 glaciers that we've looked at, but we've also expanded our methodology because we were looking at a center line before. Now we're looking at multiple flow lines across the glacier, each glacier. So we have 1,400 flow lines for 141 glaciers. And that was to account for any cross-flow variability in the geometry that might allow some flow lines to allow diffusive thinning to propagate inland and others might not. But we get the same general answer when you combine all of those together, that 90% of the observed volume loss is occurring downstream of these Peclet points of 3. And so we wanted to answer these two questions. One is, which glaciers matter most to sea level? And 2, what are the specific aspects of the geometry that really control the thinning? And I'm going to focus on this second question first. I'm going to show you 2 examples. So these are kind of like end-member examples. So this first one is Kakafat-Surmiat. This is a glacier on the eastern coast of Greenland, northeastern Greenland. And this is the mass-conserving bed underneath that ice here. And then this is the exposed bed over here. The grounding line is in white. And we've added 6 flow lines to define this glacier and colored them by the Peclet number along those flow lines. And so you can see for 2 flow lines, we have a Peclet value of 3 that's reached very close to the glacier terminus. And so if there was a perturbation, these flow lines would arrest that perturbation in this location. But then importantly, there's a whole bunch of flow lines where Peclet is less than 3 all the way to the ice divide. And we can see this in cross-section as well. So here's the cross-section surface topography, the bottom topography. The mean of all the flow lines is bolded. And then the Peclet number, again, the mean is bolded. You can see those couple of flow lines that have values that exceed a value of 3. But by and large, this glacier, if it gets perturbed at its terminus, can thin all the way to the ice divide. We can contrast this with a different example. This is Helheim, which is on eastern Greenland. And this glacier is in steeper terrain. And so it tends to focus flow and create these very deeply incised tributaries that feed into the main trunk of the glacier. There's 2 tributaries. We've dropped flow lines into each of them to characterize them, but they're both the same. I'll just show you one. So this is a kind of a different story. Here, all of these flow lines have values of Peclet equals 3 at the point where the flow line emerges from the submarine trough at roughly around the sea level location of the bed elevation. So they're all kind of co-located close to one another. And in cross-section, you can kind of see that. Here's the big step in topography, the outlet glaciers down here, and this is the inland ice. And here's where we have all these Peclet values exceeding 3 in that one location. And so we call these features knickpoints. They're similar to what you see on subaerial streams that have been used a lot in geomorphology and tectonics. And we think they're created in the same fashion. It's just differential erosion. So you have the ELA is roughly around this location, supplying a lot of water to the bottom of the ice. It's moving fast. It's causing a lot of erosion in this downstream region of the glacier where it's moving really fast, but it's frozen to the bed up here. And so it can't erode as fast. So this differential erosion causes the elevation to drop for the glacier, but it's limited at the downstream end by sea level. So it can only drop so far. And so we think that initially it drops and then the knickpoint starts to migrate probably backwards into the interior. And that's why the knickpoint is always associated with the sea level 0 location that we see in the data. And so just to look at some statistics for all of these flow lines, we see that nearly 70% of all the flow lines have a knickpoint that's located at this sea level location. And 90% of them are the same location where we predict thinning to occur by the Peclet analysis. So these knickpoints appear to be the important factor that's really limiting the amount of inland thinning that's happening. The bed for these knickpoints on average is about 2.7 degrees steeper than the submarine troughs as well. And so I want to kind of break this down a little bit to try to look at how the knickpoints are developed. And what we've done is kind of broken it into sort of qualitatively steep terrain and qualitatively gentle terrain regionally in Greenland. So it kind of goes back to these scales that I was talking about earlier. This plot here of Greenland shows all those flow lines that I showed you before, these center lines for glaciers, but they've been truncated to the point where the Pecla=3 value is located. So they're not all the same length. We have some glaciers that can thin far into the interior and other glaciers that are more limited. And so we call these areas regionally gentle topography. The range in the topography from the max to the min is smaller than what I'll show you next. And in these areas, we have glaciers that have thinning that can propagate all the way to the interior. These areas are typically, they have fewer knickpoints. So sometimes they don't have, some of these glaciers have no knickpoints associated with them. And those knickpoints, when we do see them, they're gentler. They have an average slope of less than 2 degrees. And we can compare that to steep topography flow lines. So this is terrain now that has a much higher range in topography as you go from the highest point to the lowest point in a region. These are knickpoints that are steeper on average, around 3 degrees, and they're also really co-located with one another. So they provide a really effective mechanism for armoring against this diffusive thinning from a terminus perturbation. And so we kind of borrowed this idea from an earlier paper by Mark Kessler and Bob Anderson and Jason Briner, who looked at this, at how fjords were created with a simple erosional model of an ice sheet that was this circular disc. They put a couple of passes into the ice sheet model and then watched it flow in order to create these fjords that get inserted over time. And what they found was that it's really the topographic steering of ice that accentuates, drawing ice flux into these lower locations that amplifies erosion and causes these fjords to be developed. And it's the same idea that would cause these steep knickpoints to be developed as well. So in the steeper terrain, you have steeper topography that's focusing ice flow even more, causing greater rates of erosion and larger ice flux as a result that allows for these really large knickpoints to develop. So typical knickpoints in the steep terrain have about a 1 kilometer drop. If we assume that the erosion rates are on the order of 1 millimeter a year or so, then it suggests it takes several hundred years to create, several 100,000 years to create these knickpoints. And it sort of means that, when you have these ice age cycles in the past, that they're actually really critical for setting up the geometry that's currently mitigating against climate perturbations for some glaciers. And so we want to also answer this question of which glaciers matter most, because if you can thin all the way to the ice divide, then that may be an important glacier to try to understand better. And so we're looking at those ones in that gentle terrain again. And what we see here, this is a violin plot. So it shows the distribution of these values, but it's the distance between where the knickpoint is located and where our predicted thinning inland distance would be located. So this Pecla=3 location. Now we expect them to be in the same location, right? If it's going to be arrested by a knickpoint. For glaciers in gentle terrain, that is kind of true for a lot of them, but there's quite a big spread in points for these glaciers. And I have an example of Humboldt Glacier, which is up here. And you can see this spread in points. A number of points are 800 kilometers. This is a point along a flow line, is 800 kilometers away from where we predicted thinning would be arrested from. And that's because it doesn't really have a knickpoint in those locations. And you can compare that to glaciers in steeper terrain. So here's an example showing Helheim Glacier, which is down here. This shows a much more squashed distribution, a lot more points in this location here, which suggests that the knickpoints are more co-located with where we predict thinning to occur for glaciers in steeper terrain. And so we took this idea of the inland thinning distance mattering and coupled it to ice flux also mattering for sea level. And we created this plot which simply plots those two variables against one another and then put in these phony contour lines that are qualitative, but they really just suggest that, as you go to high flux glaciers or high inland thinning glaciers, those are going to be glaciers that contribute to mass loss potential. given that they receive a perturbation. And what we see is that luckily there are no glaciers here that are both high ice flux and high inland thinning limit. But there's two kind of categories. There's a high flux glacier that has a low inland thinning limit. And then there's high inland thinning limit glaciers that are generally low ice flux. And what I want to draw your attention to are these low flux glaciers, because we're often drawn to the really high flux glaciers because they're very dynamic, they change a lot, they're massive, and people are really interested in them. But these smaller glaciers may matter just as much for understanding sea level. And so to take this a step further, we wanted to validate this work by using ISSM to test our simple theory that these, the glaciers that lacked the geometry that would arrest these thinning waves would thin more and contribute to sea level just as equally as these other glaciers. And so we modeled two end members. One is Sirmia that I showed you earlier, and this is the model domain for that glacier. This is just a blow up of the terminus position, showing that it changes over time. And we modeled basically this, we kind of moved the terminus position and forced the elevation to adjust along with it, and then let it run to 2100 to see what is the committed sea level rise from the terminus perturbations that we've already observed. Okay, and we compared that to Kangerlussuaq Glacier on the east coast of Greenland. This one also had a big retreat of about 7 kilometers in 2004. And so starting with Kangerlussuaq, this is the glacier in the steep terrain. We have the modeled topography and the terminus perturbation, the mass conserving bed here. This is the dynamic thinning that's occurred from observations. And this is using Dennis's DEM differences to get this value. And then here's our Peclet estimate along flow. We can see that when you get to values of Peclet equals 3, that we have most of the thinning has occurred downstream at that point. But when we step this forward in time, oh yeah, this is just to show that when we model the expected thinning in the time period that the observations come from, that we get a fairly decent match. So this is our estimate for the observations that we show here. And now we're going to step it forward in time and watch how the surface evolves. And what we see, is that most of the thinning is arrested in this region here. There's very little that propagates far inland. And we'll contrast that with Sirmia. This is a glacier in gentle terrain. We only have observations in this very small downstream portion of the glacier, but they match pretty well with our modeled estimate over that same time period. And if we step this forward in time, what we see for this glacier is that it thins quite a bit farther inland than the previous glacier. And so this suggests that our simple theory did a pretty good job of showing us which glaciers might matter for long-term thinning. We can look at this as a time series as well. So this is now looking at how these glaciers evolve and contribute to sea level over time. This is the steep terrain glacier, and you can see how by about 2080, it starts to level off and reach a steady state. And that Sirmia just keeps on chugging and contributing to sea level well past that, because it can drain all the way to the interior. And this is despite the fact that Kakavett has about 1/5 of the ice flux of Kangerlussuaq. And so some important takeaways are that the glacier response to climate is largely controlled by these local conditions in the geometry. And for retreat, the over deepening length is what's setting the amount of retreat. And for thinning, it's really the formation of these knickpoints that seems to matter most. These two things together suggest that glacier bed erosion is critically important for quantifying future changes. And if it can matter on these time scales, on what is the sort of smallest time scale that erosion and deposition actually matter? So I think it's an area that should be actively researched. And then the other thing is just to draw your attention to some of these smaller glacier systems, because they may also be of critical importance when we're looking at estimates of future sea level rise. And with that, I will take your questions.
Thank you very much, Ginny. So what we will do is, as usual, if you have a question, perhaps you could just put yes into the chat, and we'll get you to ask it orally. Any questions there? So far, we're just seeing applause and thank yous.
It must be really clear.
Nicholas Holsch, go for it.
Hi, Ginny. Great talk. I was just thinking about, with Greenland, there's going to be a combination of ocean-driven forcing and atmospheric-driven forcing, and thinking about how to interpret the long-term future if you have surface melt as a driver versus terminus retreat as kind of the forcing on the system. How do you think about that in the context of this framework?
Yeah, so the surface melt is going to be a much broader perturbation. It's going to happen over a much larger area. And so it would fit into the framework just the same way, but we're just simply looking at how the dynamic response goes. And I will say with this plot here, this is also just the dynamic response. We've actually taken out the surface mass balance response, and that's simply because we didn't have a great way to couple the ISSM to like what's the future climate going to be, the climate perturbations going to be to impact surface mass balance in the future. So we just ran it with modern day surface mass balance conditions and then took that part out afterwards to look at the dynamic response. So certainly it plays into it for sure. And then there's interactions between the two, which make it even more complicated.
Thanks.
Any further questions for Ginny? Laurie, go for it.
Hi, Ginny, great talk. I was wondering about the variability across the flow lines of a particular setting. So what does it take? Do you need to have everything critical across the entire fjord or just a little corner of it, or what?
Yeah, that was what we want to see in the model results. So we want to do, the model results are pretty new, or they're old, but we're still working on them. But Dennis is probably rolling his eyes right now. But we wanted to look at, if you had just a couple of flow lines that might hold back diffusive thinning, could the retreat or could the diffusive thinning propagate around that area and effectively get to the interior regardless? And so we don't really have the answer for that. I suspect that, if you had more than half of those flow lines had a bump in the bed that allowed for thinning to be arrested, that would be sufficient, but I don't really know yet.
Vijay Zhang, did you have a question?
Yes. Well, thanks. Oh, this is a great talk. I think this nicely illustrates the controls from the symmetry to the inlet thinning. So, but I'm pretty wondering, so if you're looking at the speed up or the velocity patterns, does it show the similar pattern to this control?
Yeah, you should talk to, I'm going to screw up his name, Josh Williams, I think, who's in the UK somewhere. He's looking at this. So he's got the GPS data from, gosh, what was it? When they did the survey going all around Greenland at the equilibrium line, they measured velocities over a long time period. He's comparing it to present day, and we're trying now to see if there is a match to where velocities are increasing inland. So we'd expect that if a glacier has the ability to thin far inland, that velocity increase would also extend farther inland. But I also would suspect that it would be hard to really quantify that. You'd need a lot of time to elapse in that big velocity change to really be able to measure it well.
And Shuman Misra, would you like to ask a question or?
Can lineaments also play a role in glacier stability? Does that mean like, I don't know what a lineament is. Is that like a moraine?
And Shuman, do you want to unmute yourself? And Maybe we'll come back to that. Oh, there you go. Fault line.
I don't know the answer to that question. Bob Anderson would know better. I think that he found that you can have step changes in bed topography as a result of bedrock faults. So yeah, why are the knickpoints in the places that they are is a great question. It's not clear to me that it's entirely the ELA. So there must be some other erosional factor like a fault line or a change in geometry or geology that's really playing a role there. But there's really no data to really be able to investigate that, to my knowledge. Maybe gravity, I don't know.
Olga, do you want to go ahead?
Hey, Ginny, very quick comment. The difference between the surface slope and the thickness gradient is the bed slope. So you can simplify your Pecklin number, unquote, and you get exactly the same result. So you're sort of making a circular argument that it depends on the bed slope, and what you're looking at is the bed slope, nothing more.
We have a question from Tim Bartholomew, who is on Facebook watching. Early in your presentation, when you showed the empirical retreat data, it looked as though glaciers retreated a little bit beyond the distance to the next over-deepening. Is there significance to this, or is it perhaps a result of how you define distance to the next over-deepening?
Yeah, there's a lot of averaging going on. These fjords are really complex shapes. And so what I'm looking at, when I measure the size of the over-deepening, it's sort of the, I look at the fjord, I look at the across flow variability in topography in the fjord, and then use that to quantify the bottom topography of the fjord on average across the fjord. And so it's possible it could move around outside of my defined average, if that's kind of getting at your question. But I also wonder if there could be some seasonality that might be playing into why it's retreating back but stabilizing in that location.
I don't think he can come back to us given that he's on Facebook. Oh, okay. It says thanks. Are there any last questions? I kind of feel like we've come to the end probably of the discussion. Oh, one more. No, it just says thank you. So ending in what's becoming a traditional way, if everyone would like to unmute themselves and give a round of applause to Ginny to say thank you. I'm not going to do that. It sounds too painful. There we go.
Really good to see everybody.
Thank you very, very much for the talk, Ginny. It was fantastic. And
thank you, Ginny.
Oh, and I should have said, next week's seminar will be by Eric Reno. I do not, as yet, have an advert slide for the first time. You'll have to blame my broken hand. Arm. I didn't ask for it until yesterday. So apologies, we don't have a visual advert, but Eric Reno will talk next week. So hope to see you all then.
You should lift up your hand, Toby. Okay.
Okay. Thank you very much to everyone, and thank you to Ginny, and thank you very much for the flowers. That was really, really thoughtful. Really appreciate them.
Bye.
Bye.
Thanks, Jenny. Thanks, Jenny.